This is February-March. This is February-March 2025, paper 4. These are the great thresholds. Okay, so the first question is about this ball rolling around in this cone, like an angle at this angle. He says on the figure 1.2, draw the arrows to show two forces. Now the first force is very obvious and evident, that the weight that's going to be downwards, labeled mg, or you can simply label as w. The next force is normal reaction, which will be at a 90-degree angle from the surface, which we always draw like this, and I'm going to remove this for the understanding. This is the normal reaction. Now it says draw the arrow for two forces. He says describe how the forces acting on the ball cause an acceleration to be centripetal. Now the vertical component, which is equal to the weight, is actually going to come from the normal reaction. There's one component for the normal reaction that is in the upward direction, and one of them is going to be in this direction. But for the sake of simplicity, I'm going to draw this somewhere here, like this. And due to geometry, you can find out that this is going to be normal reaction, cosine of 52, and this will be normal reaction, sine of 52. This is equal to the weight. And since they are equal, the ball is neither falling down, it's neither gaining height. It means that these two forces must be equal to each other, which is what he says in the answer, that the vertical component is equal to the weight. Hence there is no resultant in this direction, which means that the ball is not going to move in this direction, or is not going to experience any acceleration in that direction. The next property is horizontal component towards the center of the circle provides the necessary centripetal force and centripetal acceleration, that is this one. So nr sine 52 is responsible, or is pointing towards the center of the circle, that is going to cause it to move in a circular motion like this one. So let's move on. He says that the ball moves in a circle of the radius this much with a speed this much. So okay, fine. He says show that the speed is 1.4. Okay, no problem. So first let's look at the components. So the first component we have is normal reaction, cosine of 52, which is equal to mg. And then normal reaction, sine of 52, which is equal to the centripetal force, which should be mv squared divided by r. Now if you divide these both equations, so let's say this is equation number 2, this is equation number 1. If you divide equation number 2 with 1, you get nr sine of 52 is equal to mv squared divided by r whole divided by normal reaction, cosine of 52 equals to mg, and nr cancels with nr, sine divided by cos is tan. Due to mathematics identity, this will become tangent of 52 equals to m cancels with m, and we are left with v squared divided by rg. We've known that the acceleration is equal to v squared divided by r. We can replace it here somehow, but at this stage let's avoid doing that. So okay, the next part of the system would be to simply find out that, for example, that this is tangent 52 is equal to v squared divided by rg. Now everything is given to you. We wanted to show that the velocity is equal to 1.4. So let's see what's what. The radius of orbit is 0.15, g is 9.8. Let's take everything on the other side, and don't forget to take the under root of this equation. So we are left with r, which is 0.15 multiplied by g 9.81 multiplied by tangent of 52 degrees equals to v squared. And if I replace the v squared from this side, take it to the other side, or you can say taking the root on both sides, this will be transferred like this. So the velocity's answer comes out as 1.37 meters per second, which up to two significant figures is 1.4 meters per second. Calculate the angular speed omega of the ball, which is very simple. That is v equals r omega. V was known to us, which is 1.4. R is 0.15. Omega is what's supposed to be found. Omega is equal to 9.33 radians per second. So this will be 9.3. It's a recurrent decimal place. Up to two significant figures, that will be 9.3. The next question is, he says, explain why the radius of the circle orbit increases if the speed of the ball increases. Now there's a bit of a mathematical understanding behind this. You have to go back to this equation, which was tangent 52 and this one. Let's rewrite it for this part. So we had the equation as tangent of 52 equals to v squared divided by gr. You take everything on the other side, the equation looks like this. So tangent of 52 or tan of 52 multiplied by g multiplied by radius is equal to v squared. Now these factors are constants, so the equation comes out as v squared being proportional to r. So if you increase the speed of the ball, the radius of the orbit also increases. All right, so that is why it's going to work like this. That's why we say the centripetal force is not changing. Everything is almost same, and the acceleration, centripetal acceleration, is also not changing. So v squared proportional to r, that's how we get this. And since the speed increases, the radius also increases. Part 2, he says, sketch the graph. It's a very common question. It's repeated again and again. So I've given you a table on the left side, on the right side. So this is phi equals to gm over r, if you remember, with a negative sign. Now, how to draw these graphs? I've explained this many times. Since phi is inversely proportional to 1 over r, what we can do is just replace values in this. So if r was 1, 1 divided by 1 gives you 1. So phi is 1. So we work this way back. If r is 2, this becomes 1 by 2, or phi becomes 1 by 2. This becomes 1 over 2, which value is 0.5. If r is 3, work your way back, that becomes 1 over 3, that becomes 0.33. If r is 4, that becomes 1 over 4 and goes up to 0.25. And of course we have 4r over here, so let's replace these values. Now since it has to be with a negative gradient, it's going to be with negative values. So on the surface r, when r is 1, phi is also 1, so this is one coordinate. When r is 2, phi is supposed to be half, 0.5. That's the second coordinate, and so on and so forth. That's how we draw the rest of the coordinates. So at this moment, 0.33, please count this property. This will be 6.6 boxes, so this will be somewhere around here. And 0.25 is 5 boxes, will be somewhere around here. And then you draw a smooth line through all these points. You might be better at this, so let's keep practicing. Okay. Now, let's move on to the next question. He says, draw the graph of gravitational potential. Now, gravitational potential, since the height or the location of the satellite is not changing, the gravitational potential energy will also not change. So that's why it will have a constant value of negative phi, for example, at this place. It's not changing, so it's going to be a straight line. The height is not changing, that is why it's going to be this line. Moving on to part C, he says there's electric potential, and if it's positive, let me give this an arbitrary value. Let's say that this is plus 1000 volts. Since this is a symbol for ground voltage, this should be 0 volts. And that's just for reference. Moving on to the next graph, he says, on figure 2.4, sketch the variation of electric potential with distance from the positive plate. Now, if a charge is close to the positive plate, we will experience the highest potential. Because potential or electric potential is the work done to bring a charge close to this plate. And if you're looking at the test positive charge, this plate is also positive charge. It's going to take a lot of effort in order for us to be able to do that successfully. Which means that if you're very close to the positive plate, the potential will be very high. In order to get very close to the positive potential plate, it's going to take a lot of effort. So that's why the value is very high. But since the distance is being measured from the positive plate, the reference is from the positive plate, it means you're going away from it, or your reference point is slightly away from that point. You're not coming as close to this as you are likely going to be. So the last coordinate will be over here. So this makes it into a straight line, which is going to look like this. Eventually look like this, right? Okay. There's one thing that sometimes confuses students. Electric potential was the work done. Certainly it is Q divided by R, right? Or distance, okay? And this K is definitely 1 over 4 pi epsilon naught. We're not getting into constant. We're thinking about the electric field. What will the electric field be between the planes? So it will always be constant, because the formula for the electric field is potential difference divided by the distance. The potential difference is not changing, the distance is not changing, so the electric field strength is definitely the same. This is just on a side note, not part of the paper. Question number 3, he says, two objects are in thermal equilibrium. How do you define a thermal equilibrium stage? You simply say that the object P and Q are at the same temperature, whatever temperature that may be, and there is no net transfer of thermal energy among them. When we talk about net transfer, it simply means that, for example, if this is P and this is Q, and they're both at 20 degrees centigrade, this is also 20 degrees centigrade, and in perfect isolation, there's nothing coming out, nothing going in. They are losing energy. P is also losing energy, Q is also losing energy, but they're also gaining it back. So the amount of energy they're giving out, they're also getting it back, which is why when we say net transfer, this is important to understand that it doesn't mean that there is no transfer. The transfer is happening, but the resultant effect is zero. It's kind of like saying something like this, that there is an object with 200 newtons of force right side, 200 newtons of force left side. These two forces are still acting. They do have their individual identities. One is to the right, one is to the left, but the resultant force is zero. The resultant force zero, the net force being zero, does not justify or does not nullify the existence of these two forces. It just means that they are not good enough to produce a change. Data for P and Q are given to you, capacities are given, masses are given. He says that some energy is supplied to P and they're in perfect isolation. Once again, they both have the same temperature eventually. P and Q are perfectly insulated from the surrounding, which means there is nothing coming out and in or going out from the external surrounding. So he wants to find the delta T of Q. Now, is it different from P? Now, for that, we need to understand what may be going on. Let's say that the object P, this is P, and this is object Q. It's possible that they're joined together. It's possible that they're separated. What we are doing right now is providing 24,000 joules of energy just to P. And of course, if you provide thermal energy to P, its temperature is going to rise up and it will release its energy in terms of radiation, conduction, any method that there's possible in that situation, but it's going to release that energy which is going to be gained, or some of it is going to be gained by Q. So at the end of the day, whatever 24,000 joules can bring in, whatever delta it brings in, the same delta will be experienced by Q, but they all have different specific heat capacities. Then how do you justify this? They have different masses, different heat capacities. How do you justify this? Now, since we are saying that they end up with the same temperature, it means that their delta T's should be the same. Now, how it may be happening? Again, this is just one scenario. For example, that this is object P, this is object Q, and this is a scale for temperature. Let's say 1, 2, 3, 4, 50, 100, 1000, whatever scale of temperature this is. At the beginning, the temperature of P rose very quickly, and Q was following it very closely. But at some moment, you stopped heating it up and it stopped rising. So P started to come back down again, or started to cool down, but Q was still heating up. Why P is cooling down? Because P is still releasing the energy that it gained back, and Q is still gaining that energy that the P is releasing right now. So there will come a time when they will eventually collect at a single temperature, which means that if you look at this from the starting point, their delta T's are exactly the same. Definitely, P has had a different journey than Q, but their changes in temperature are exactly the same, because they're going to settle down at a simple or a common final temperature. They started their journey at a common temperature, they ended their journey at a common temperature. Hence, their delta T will be exactly the same. Based on this logic, we simply said that the energy given into the system should be equal to the energy contained by P plus energy or thermal energy contained by Q. The energy brought into the system was 24,000 joules. The energy taken by P is mc delta T, and by Q is mc delta T as well. So it's just a matter of replacing values. So this will be 24,000 equals to mass is given to us in the table, which is 0.54 into 390 into delta T, plus 0.37 into 910 multiplied by delta T. This is why delta T is exactly the same, because they've had the same journey at the end of the day. So consider delta T as a variable X, for example, and then you solve for T. That comes out of 43.8 Kelvin, which will be 44 up to two significant figures. Part B, he says that we have a volume of gas, an ideal gas at a constant temperature of this fixed amount of gas, which means that there's no leaking. The number of moles are exactly the same. The variation V of the volume is given to us, and the degree centigrade is also given to us. Most likely this will be PV equals to nRT or nKT. But let's see which one is this. He says determine the work done on the gas from 0 to 210. Now from 0, this value is 0.18. And at 210, please read this carefully, this will be 0.32. Now from the looks of it, based on thermal energy addition, it looks like that the gas has expanded. Now, I've based this on my previous lectures. If the gas expands, the work done generally is negative. And the logic behind is this, that the energy provided through the thermal energy has been used up to push against the atmospheric pressure, which means that that energy is not a part of the system anymore. Whatever energy you brought in as thermal energy by increasing the temperature has been used up by expansion. That's why it is with a negative sign, which means it doesn't belong to the system anymore, because the gas has pushed against the atmospheric pressure or the external pressure wherever it was present. And that pressure in this case is this. That's why it's going to be a negative sign. And for your understanding, I've added a table over here. Whenever he says work done on the gas, as he's mentioned here, if it expands, the sign will be negative. If it compresses, the sign will be positive. Because the compression logic is that you have added energy into the system because you can get it back. Much like the piston of an engine. When you compress it, you can take that energy back as well. But if it says work done by the gas, it's just a perspective change. It's just a matter of English, that when he says work done by the gas during expansion, you have to put a positive sign and a negative sign. I haven't been able to find a question that does this, but I have added those questions for you, for your reference, so you can practice your knowledge about work done on the gas or by the gas, expansion or compression. So logically, this will be work done into P delta V. The external pressure this all happened against was 1.6 power 5 into simply 0.18 minus 0.32. You can put this the other way around as well, final minus initial, but you need to realize that the answer will be negative. It should be negative 2.24 into 10 raised to power, sorry, it's not 2.24, it's going to be 22,400, which you can definitely convert this into standard form. So this will be negative 2.2 into 10 raised to power 5 joules. It says determine the number of nitrogen molecules. Now you can simply use the equation, which is PV equals to NKT. Now the pressure is definitely 1.6 power 5. V is 0.18 equals N, which we don't know, and K is Boltzmann constant, 1.38 power minus 23. Temperature should be in Kelvin, so this will be 0 plus 273. Now notice that if I'm taking 0.18, I'm taking temperature as 0. If you were taking 0.32 over here, then the temperature should be 210. So if you wanted to solve this with other credentials, the only change here should be 0.32, and the only change here should be 210 plus 273. But mind you, that if you solve this with this equation, your N will come out as 7.64 into 10 to the power 24. But if you solve this with this, your answer comes out slightly different, which is N equals 7.68 into 10 to the power 24. If you round off your answer based on this, it will be 7.6. If you round it off based on this, it will be 7.7. Now there is some difference with this. I haven't been able to find a reason, but if you know the reason why there is slight different and why would the examiner accept this method, please let me know in the comments, and we can add information to other students coming to this video as well. The mass of nitrogen molecule is this. They calculate the RMS speed of the nitrogen molecule at 210. So basically what he's trying to do is trying to make sure that you understand that temperature is representation of the speed of the gas molecule. And that is what temperature is. We perceive that as hotness or coldness, but it's really just telling us the speed of the molecule, the temperature, if you look at it. So the basic idea would be half mc RMS square is equal to 3 by 2 kT. And the idea comes from this, that the temperature of any system in Kelvin is actually proportional to the kinetic energy of the molecules, which is proportional to the speed of molecules. Why do we land on speed? Why do we think about speed? The idea is that if you look at the form of kinetic energy, half mv square, you cannot change the mass of the atom, nitrogen, carbon dioxide, oxygen. You cannot change the mass of that specific atom. What you can change or experience a change is in its speed. So temperature eventually leads to speed. Anyways, let's put in the values over here. So this is 1 over 2. Mass is given to us as 4.7 into 10 raised to power minus 26. I think it's given over here, yes. And the root mean square, CRMS value, square is not known. 3 by 2 Boltzmann constant is 1.38 into 10 raised to the power minus 23 into 210 plus 273. And luckily, of course, don't forget to take the under root or square root on the other side. The CRMS comes out as 652.26 meters per second, which up to two significant figures will become 650 meters per second. Let's move on to question 4. He says that a small cylinder is based, and of course this question is from simple harmonic motion. This is your mean position and this is your extreme position. This will eventually become your x naught or amplitude, and the rest of the positions will become your x or current displacement. He says show that the angular frequency is this. It's very easy to figure this out because omega is not only equal to 2 pi f, but it's also equal to 2 pi by t. And we can easily figure out the time period on this graph, which is this 0.15. So this is, the one thing that's missing on this is a misprint probably. The time is in milliseconds. So be careful if you pick out this time, this will be 1.5 milliseconds. So omega is equal to 2 pi divided by 1.5 into 10 raised to the power minus 6. When you do that, your final answer comes out of omega as 41.88 into 10 raised to the power 7 radians per second, which of course up to two significant figures is 4.2 into 10 raised to the power 7 radians per second. Now I just made one mistake. This is not 7, this is going to come out as 6. Apologies for that. Okay. Maximum acceleration, and for maximum acceleration we understand that it should be at the displacement itself for the maximum value. So this is acceleration naught is equal to negative omega square x naught. The maximum amplitude, which is of course can be read from the graph, which will be here or here. So if you read it carefully, this is going to be 40 or this is also going to be 40. So the omega square was calculated for in the previous part. Now please be advised if you ever face any difficulty in any part and he says that show that the value is this, be advised this will be used in the next part. So even if you fail to do this, please don't forget to do the next part because it's free marks, even if you lose some over here. Don't just lose hope and give up on the whole question. So minus, we can ignore the negative over here because it only represents direction. So this will be 4.2 into 10 raised to the power 7 into x naught, which is the displacement, maximum displacement, 40 into 10 raised to the power minus 6. Because if you can see from the graph, it is minus 6 over here. So this comes out as 7.1 into 10 raised to the power 10 meters per second square, because acceleration. So 7.1 into 10 raised to the power 10. Please make sure that you're doing the correct calculations using the calculator. He says determine that the energy E of the vibrations, the mass is given to you. Now, since he's talking about the total energy can be found by two ways, either through total gravitational potential energy or through total kinetic energy, because at 3 instants they exchange each other's energy as we've seen in a pendulum. So if I want to find the total energy, I can simply find out the total kinetic energy, which will be half mv square, and v is equal to omega under root plus minus x naught square minus x square. So let's replace this over here and we get our new formula, which is 1 over 2 m omega square bracket x naught square minus x square. Since I'm looking for maximum kinetic energy, because I'm looking for the total kinetic energy, the x becomes 0. This part becomes 0. So really I'm left with the equation half m omega square x naught square, or the amplitude square. So I've just a matter of replacing values. 1 over 2 into mass of the system or the pendulum is 2.4 minus 4. 2.4 into 10 raised to the power minus 4 into omega square. If you go back to the omega, this is 4.2 again. I remind you that even if you weren't able to show this part, this will be used in the next part. So 4.2 power 7, 4.2 into 10 raised to the power minus 7, sorry, positive 7 whole square into x naught square, which is 40 into 10 raised to the power minus 6 squared. Now once you calculate this carefully, this is going to come out of 338 joules, which will be 340 up to two significant figures. Part D, he says the crystal generates an ultrasound wave that is used to obtain diagnostic information. He says crystal is made from piezoelectric material. He says explain how the crystal is made to vibrate. We do this by applying an AC current to it, or AC voltage to its faces, and based on that voltage difference, or based on that alternating voltage, it changes its shape. So we simply state what's actually going to happen. So applying alternating potential difference across the crystal causes it to change its shape or causes it to distort. If he had asked you about ultrasound production, then of course we're going to lead into compression and rarefaction, but we're going to stop here because he's already asking us to vibrate the crystal. Then he says a parallel beam of ultrasound XYZ, he says calculate the percentage intensity of the ultrasound beam transmitted. Now the formula that you do in your classrooms is reflection coefficient, which is Z1 minus Z2 divided by Z1 plus Z2. This is about the reflection. You see, on a boundary, for example, if this is the boundary, this is your skin, and this is your muscle or tissue, and this is what the ultrasound or the initial I0 ultrasound intensity is. There's going to be one wave that is transmitted, let's call this IT, and there's going to be one wave that's reflected back, IR. The formula that we do over here is actually a ratio of this. It's not a ratio of this. So what we do assume is that if this was 100%, and let's say we get back 40%, then 60% must have been transmitted in. These are just hypothetical values for this given case, but let's move on with the values. This is acoustic impedance, and the way to solve this or to find this is that Z is actually equal to density multiplied by the speed of the sound in that material. So just multiply these two numbers together, you get the acoustic impedances of sound, ultrasound, in those mediums. So the muscle value is going to come out as 1760000, and the bone value comes out as 7790000. And if you cancel out the number of zeros, this narrows down to 1.76 and this to 7.79. If you're not happy with this cancellation, you can take full values, but it will add to the mathematical inconvenience, so I've just avoided that. So let's find out the reflection coefficient first, how much is reflected, because if I have that information, I can then simply subtract it from 100%, and then I can get the transmitted wave. So a reflected wave divided by the original wave should be equal to Z1 minus Z2 divided by Z1 plus Z2. Now naturally you might be confused about this one thing, that which one should be Z1, which one should be Z2. The fact that it's being squared doesn't really matter, because even if you subtract 1.76 or 7.79 from 1.76 and you get a negative answer, the square will take care of this and it will give you a positive answer. So it doesn't really matter. So this will be 7.79 minus 1.76 divided by 7.79 plus 1.76, and of course don't forget to take the square. So the reflection coefficient I0 comes out as 0.398, which becomes 0.4, which becomes 40%. Now this means that out of that 100%, 40% got reflected back, is coming out, is going back to the same skin, going back to the same tissue. But if this was 100% sent to the skin boundary, then it must be true that 60% is still being transmitted. So this is our reflection coefficient. This helps us figure out what's coming out, what's being sent back, so we can figure out what's actually going in or being transmitted. So 60%, if the I0 is 100%, 40% came out, we are still left with 60% that was transmitted in. That's why this is 60% or 0.6 if you want to consider the fraction. He says capacitor is given. Now we want to prove this relationship. It's very easy. Basically, if this is for a series combination, as he mentions here, the total charge coming from the battery is equal to charge on the first capacitor plus charge on the second capacitor. Not plus, is equal, sorry. It's supposed to be equal, because there is no way for the electrons to go through. So no matter the size of the capacitor, if the battery has sent in 10 electrons, the 10 electrons will show up on Q1 and 10 electrons will show up in Q2, because there is no connection between them. That's why they're equal. And since it's a series combination, the voltage is divided. So the voltage from the battery total voltage is equal to V1 plus V2. We have an equation which says Q equals to CV, and since we're replacing V in this equation, so this becomes Q divided by C equals to V. Let's replace this into this equation. This becomes Q, total charge divided by total capacitance, equals to Q1 divided by C1 plus Q2 divided by C2. Now we've noticed that based on this equation, since all the charges are equal, QT, Q1 and Q2 gets cancelled out from this equation, and we are left with, finally, 1 over total capacitance is equal to 1 over C1 plus 1 over C2. And that's how capacitors in series get solved, and that's the logic behind them. He says the combination is given to you, and just to figure this out, if I want to replace a whole network with a single capacitor, that will be, if these are connected in series, this will be 0.5 C. If you want to solve this properly, this will be 1 over 1 C plus 1 over 1c equals to 1 over c total. This will come out c total as 0.5c. But I'm not considering the c at this moment. And if they are in parallel with this branch and this branch, parallel branches get added together. So this will be 1c plus 0.5c. So the capacitors between terminal X and terminal Y, it looks like that the combination is effectively 1.5c. The graph for charge and voltage is given to you. We're going to use that in the next part. It says show that C is equal to 44 microfarads. Now, we're going to begin with this equation, which is the total charge Q equals to CV, the total charge in the system stored at this potential, because he says that this is between X and Y. The battery doesn't know that there are 3 capacitors. The battery thinks that there is only one, which is equal to 1.5. So it stores from the graph, the maximum store it has been able to store is 400 microcoulombs at 6 volts. So this is 400 into 10 raised to the power minus 6 equals to capacitance, which we don't know, multiplied by 6 volts. So the total capacitance, which is of course equal to 1.5C, this CT comes out as 6.66 into 10 raised to the power minus 5 farads. And of course, since this is equal to 1.5C, we're just simply going to divide 1.5 with this, and we're going to get C. So 1.5C is equal to 6.66 into 10 raised to the power minus 5. Since I'm not at the final answer, I will prefer to take more than 2 or 3 decimal places or full values. So C is equal to 6.66 divided by 1.5. This leads to 4.44 into 10 raised to the power minus 5 farads. Now, since it's asking us about micro, you push a button and you get to micro by moving a decimal place here. So this C is equal to 44.4 into 10 raised to the power minus 6 farads, which of course becomes 44 microfarad as asked by the examiner for us to show. Then he says the capacitor network 5.1 is charged fully and then connected to a resistor 54. Determine the time constant in the very basic form. Time constant is RC. Time is what we don't know. Resistance is 54,000 because this is 54 kilo. The capacitance is very much so 6.66 into 10 raised to the power minus 5, because over here he's asked us about the single capacitor. So if you go back to the circuit, it looks like that this is 44 microfarad, this is 44 microfarad, this is 44 microfarad. Now if you want to work your way back to the total capacitance like this one and get 6.6 again, be my guest, but you don't need to do that because you know that the full combination, the whole tank of capacitor charge is 6.6. So over here, that's why we are using this, because we want to see the full bank of capacitor being used. So the time period comes out, or the time constant comes out as 3.59 seconds, which will be 3.6 seconds a unit. I said determine the time taken for the discharge current to reduce to 15% of its initial value. This is what an exponential decay looks like. If this is, let's say, 100% of the charge, 15% is going to be somewhere around this side. So 100% is I naught, and this is the current I. The equation actually goes like this: I equals to I naught, e raised to the power minus t divided by RC. Now time is of my choosing. I choose the value of t. RC is the time constant, that's fixed, that's 3.6. I naught is the initial value, that's 100%. I is the current value, which is 15%. So if I simply take this over the other side, this becomes I divided by I naught. In reference to the I naught, I should still be 15%. That's why this is being replaced as 0.15 equals to e raised to the power minus t divided by RC. Now from this point onwards, it's just your mathematics skills. We know that taking a natural log on both sides eliminates e and brings this on the outside. So this becomes ln 0.15 equals to negative t divided by RC, and RC is 3.6. So I'm going to simply replace that over here. This is 3.6. Now, don't be confused by this negative sign, because when you calculate this natural log, it's also going to produce a negative value. So both negatives cancelled out. This leaves us with 1.897 equals to t divided by 3.6. Again, you get negative on both sides, they get cancelled out, which is why I've not written this down over here. So again, t will be equal to 6.829 seconds, which is 6.8 seconds in total, which means that if we had waited, for example, for 6.8 seconds, this capacitor system would have discharged its energy or discharged its current through almost 85% of its initial current to get to 15% current in a time of 6.8 seconds. If he started the stopwatch here, until he reached here, 6.8 seconds would have passed by. Question number 6. It says an electric field is set up. Okay, path of ions, positive, negative, everything is given. There's a magnetic field between them. There's electric field and magnetic field. The potential difference is given. Everything is given. He says, show that the velocity selection can be done with this. And the only thing is that they've selected speed as u because it gets mixed up as v with voltage. So the idea is that your first starting step would be that the electric force, Fe, should be equal to the magnetic force. Only then this beam of ions will be able to escape unfazed or unchanged. So the electric force comes from QE, from chapter of electrostatics. Magnetic force comes from force on a charge, QVB. Now this V is the velocity, so I'm going to change it at this stage to avoid confusion later. Q gets cancelled out, with left with E equals UB. This is the speed given to us. In the book, it's usually B. It's usually V. Now, electric field strength, because it's being between parallel plates, is given us as voltage divided by distance equals 2UB. Now, since he wants us to make U the subject of the formula, we take B on the other side, so we are left with U equals the potential difference, capital V, divided by BD. So hence we've shown how this works. Now it gives us that the positive ions have a kinetic energy this, mass this, voltage this. He says, and D is also given. What he wants us to do is find the B. So let's simply use this formula, which is going to be U equals potential difference divided by BD. Now since we're given the kinetic energy, let's put that into the perspective as well. So this will be kinetic energy, which is EK equals 1 over 2 mv square. Kinetic energy is given to us as 4.1 power minus 17. So this will be 4.1 into 10 raised to the power minus 17 equals to 1 over 2. Mass is given to us as 3.2 into 10 raised to the power minus 27 into, now since V is not given to us, this was velocity square, is given to us in the previous part, right? Let's use that formula because we have potential difference over here, we have D over here, and we're supposed to find B. So that's going to come over here straight away. So this will be 980 divided by B multiplied by 3.6 into 10 raised to the power minus 2, bracket close, and all of this, since it's velocity, this has a square on top of it. So when you rearrange everything, this gets multiplied, this gets divided, and then the under root gets settled for this. Your final answer for B should come out as 0.170. Please perform the algebra correctly. This will be 0.170. Everything is given to you. Part C. He says a proton passes, okay, undeviated from the velocity selector, but an alpha particle enters the same speed as a proton. State how the expression A predicts the path of alpha particle also passes undeviated. You see, the equation actually looks like this, that this is U equals to V divided by BD. None of these variables depend on the mass or the charge of the particle that is being accelerated. Hence, it is independent, which means that it doesn't matter. That's why alpha also passes undeviated. He says reference to 6.1, and to forces acting on the positive ion determine the direction of the magnetic field. You see, if we look at this from the perspective of a positive ion, which is trying to move in this direction, this is its velocity, entry velocity. The electric field or the electric force, since the upper plate is positive and the lower is negative, the electric force is downwards. Because the lower plate is negative, the top plate is positive. The electric force is downwards. If it is passing undeviated, which means that it should be, the magnetic force should be in the upward direction. And definitely so, they should be equal. If that is the case, you have to apply the Fleming's left-hand rule, as from GCSEs and O-level days. The first finger is going to represent the direction of the magnetic field, which we don't know at this stage. So let's open up the second finger. The second finger opens up directly towards this side, matches the direction of the velocity, and the thumb opens in the upper direction, which is the force, magnetic force given by the examiner. If you notice that once you've done this, your first finger should be pointing into the screen. This is where you're standing. Your first finger should be pointing towards the screen of the laptop, or the screen where you're watching this video, which means that the magnetic field is actually like this. The magnetic field is into the page. So that's how you justify that the magnetic field is into the page. You explain everything, and then according to Fleming's left-hand rule, you just conclude that the magnetic field is into the page. He says a positive ion enters which velocity selector with greater kinetic energy, which means the speed will be higher. sketch the part of this. So the equation was, or it comes from the fact that the magnetic force is equal to the electric force. The electric force is QE, magnetic force is QUB, charge cancels out, we're left with the UB equals to E. Now, if you launch this at a higher speed, because of greater kinetic energy, if you launch it at a higher speed, the magnetic force increases as opposed to the electric force, because electric force depends on the electric field strength, which is V divided by D. We haven't changed the potential, we haven't changed the distance, so the electric field strength is still the same. So the electric force is still the same. The only thing that is going to change is the magnetic force, and we know that electrons or charges moving in a magnetic field experience a force. So over here, if you've introduced a charge, the magnetic force it experienced was in the upwards direction, the electric field was in the lower direction, because this is still a positive charge, it's still a positive ion that is being introduced. The magnetic force will dominate because of higher velocity, so it's eventually going to go in the upwards direction, slightly curved in the upward direction. Question 7. State Faraday's law of the electromagnetic induction. Magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux or flux linkage. Again, definition from GCSE O levels. A metal rod is accelerated uniformly accelerated. This information will be important later. Keep that in mind. In the magnetic field like this, he said the rod has a length L, flux density, and everything is B. EMF is induced in the rod. That's definitely going to happen. And with time t of the induced EMF E. So it took 2 seconds. Or for 2 seconds, if you keep it moving, it will generate an EMF 3.3. He says explain 0 using figure 7.2. The E, that E is proportional to the velocity. There are 2 stages to this question. The first one is, since the rod is being accelerated uniformly, the velocity will be proportional to the time. So even if you consider that the initial velocity is 0 or it has some value, you can see that as if it is a uniformly accelerated motion, as time passes by, the velocity increases. So we can say, and since the acceleration is constant, we can say that the velocity is proportional to time. That's the first bit. From the figure 7.2, we can also clearly see that EMF is proportional to time. Now we developed this logic that since both are proportional to time, they must also be proportional to each other, which means that that's why we've landed to this conclusion that EMF is proportional to velocity. That's how they've done it, because they are both dependent on time. This comes from graph, this comes from this equation. Okay, use Faraday's law to show that now this is a bit tricky. It's going to take a little bit of variable manipulation, but no worries, we're still going to do this. So the standard EMF was equal to the rate of change of phi divided by change in time. Now this delta t and this t are 2 different things. Please be advised. If you remember, this is basically the per second thing. In 1 second, what's going to happen. And for phi, we have the formula BA, and this is still delta t. B is simple, delta t is simple, is the A that creates the problem. Now, since we go back, let's say this rod is moving through this magnetic field, and in 2 seconds, it sweeps out this area, this cross-sectional area has been swept out by this conductor. And this is one side of the conductor, which is the length, and this is the other side of the conductor. That's the problem. This is what we want to figure out. So in a time of, if you want to find the distance of this, in a time of, let's say, the speed equal to distance over time, in a time frame of t seconds, which is 2 seconds, with some distance, whatever this, with some speed, for example, and whatever distance it has covered, the distance will be equal to speed, which is velocity, multiplied by time. This is what it will come down to. And we know that the velocity was actually equal to AT from the previous conclusion that we just made. Sorry, not that, but yes, this is where we got the conclusion from, right? So we are left with these 2 equations. So let's put them into the cross-sectional area. How are we going to find out the cross-sectional area? This is going to be area, or cross-sectional area, equals to simple line length 1, L, multiplied by AT, because that's V, the distance, which is equal to V dot T. If you put this here, this will be AT multiplied by T. And this T is definitely the time spent in that magnetic field, okay? Or the change per second. So this will be L multiplied by AT multiplied by delta T. Now this is the cross-sectional area. Let's take it back to this. This will be B multiplied by simply L multiplied by AT for the velocity's sake, multiplied by delta T spent in that duration. time duration, divided by delta t still. So delta t cancels out with delta t. You're left with BLAT, that's given in the question. Okay, even if you're unable to solve this part, you will still get credit for this mark. You'll still get credit for using this equation in the next part, so please don't lose hope. The length of the rod is given to you, the acceleration is given to you, the value of b is supposed to be found out by using that equation. So we will have to go back to the graph and we will have to pick out the value. So this is EMF equals to BLAT. EMF from the graph at the maximum value 0.3 into 10 raised to the power minus 3. If you go back, this is what it is, 0.3. Okay. I think it's not 0. It shouldn't be this. Yeah, it will be just 0.3. Okay. All right. So this will be then B into L is 0.45 into A is 7.8 into T is 2 seconds from the graph. So B comes out as 4.273 into 10 raised to the power minus 5. It should be this. So it's actually misprint over here in the table. This should be milli. Okay, so there's no misprint. This is milli. So this should be into 10 raised to the power minus 3. That's my bad. So this will be 4.3 into 10 raised to the power minus 5. Okay, question number 8. He says, what's a packet of photon? Is again, this has been a repeated definition. So this will be it's a packet or quantum of energy that belongs to an electromagnetic spectrum. A fixed definition, memorize it. It's nothing too difficult. He says that calculate the wavelength at this energy. Simple formula, E equals to HF, which is equal to hc divided by lambda. So this will be 1.96 into 1.6 into 10 raised to the power minus 19. The way we're doing this is converting electron volts into joules. So H is 6.63 minus 34 multiplied by speed of light, which is 3 into 10 raised to the power 8 divided by lambda. Let's find lambda. Lambda comes out as 634 into 10 raised to the power minus 9 meters. And up to 2 significant figures, this becomes 6.3 into 10 raised to the power minus 7. He says the power of the beam is this, the number of photons emitted per unit time in 1 second, as opposed to the unit given to us as well. So this will be power equals to energy divided by time. Power is 1 into 10 raised to the power minus 2. Energy is what we're trying to find out, or is given to us about the 1 photon, which is 1.96. So 1 photon brings in 1.96 into 1.6 into 10 raised to the power minus 19. So how many number of photons should be emitted per second, or in 1 second? So it should be something like this. The total photons multiplied by the energy of the photon divided by T, which is 1. So your N comes out as 3.188 into 10 raised to the power 16. This becomes 3.2 into 10 raised to the power 16 photons being received in every second. Now this part is interesting. He says that to determine the average force exerted by the beam of photons on the surface, this concept actually comes from the idea of radiation pressure. Do some research on this. This is an interesting concept, this interesting idea. Radiation pressure. He says that the photons are incident normally on a surface. Half of the number of photons are absorbed by the surface, half are reflected. Let's visualize this. So the momentum of photons is given us by the equation E energy divided by C. So, and this is of course an equation that you have to memorize. This is, let's say, the surface that we're hoping to find the equation for. There are photons, and I've split them in two because he says that half of them are doing something else, half of them doing something else. So n by 2, or half of the photons, have been completely absorbed. Whatever momentum they had has been converted into 0. So the change in momentum has been p minus 0, which is p. For the rest of them, which was again n by 2, half of the photons have actually been reflected back like this. So the brought in momentum positive p, the reflected back momentum should be negative p, and the change in momentum for this stream should be final minus initial 2p. So half of them are doing or experiencing momentum 2p, half of them experiencing p. So that's going to be calculated accordingly. So the idea, the theory behind this would be that the force exerted by them should be equal to delta p divided by delta t. Now since we're dealing with the per unit time, I think it's mentioned here, per unit time in 1 second, so delta t becomes 1. But that's not the issue at this moment. The issue will be delta p. So delta p will be equal to delta p plus 2 delta P. Why? This is the first stream, this is the second stream. So let's replace those values based on this. Okay, so first the energy is 1.96 into 1.6 into 10 raised to the power minus 19, converting electron volts to joules, into 3.2 into 10 raised to the power 16 divided by 2. Why? Because it's the first half of the stream, and of course this is being divided by the speed of light, which is 3 into 10 raised to the power 8. This was the first stream. This one is done. Now the second stream is going to be calculated over here. So this will exactly look exactly the same. This is this, and this. So 1.96 into 10 raised to the power, 1.96 into 1.6 into 10 raised to the power minus 19 into 3.2 into 10 raised to the power 16, positive 16, divided by 2, divided by 3 into 10 raised to the power 8. Now there's one twist to this. You see, this is momentum for just one stream. This one experienced 2 times the change of momentum. So the whole equation, this one, the whole second part, will be multiplied by 2. Okay, so your final force answer comes out as 5.017 into 10 to the power minus 11 newtons. If you solve the whole equation in one go, this is what you will get. But the answer will be 5.0 into 10 to the power minus 11. Now just notice how much force these photons are exerting on any surface they hit. This is called radiation pressure, or force because of the radiation. Now why pressure? Because of course they're exerting a force on this surface area, so force over an area becomes a pressure. And please do some research on this. It's an interesting topic. Question number 9. He says it's from radioactivity. What is meant by random? It is impossible to predict which nucleus and when that nucleus will decay, spontaneous. It's not affected by external conditions, for example, adding temperature, raising temperature, cooling it down, adding acid or base, adding some other chemicals, or adding force on this, or applying a force on this, suddenly applying a force on this. It doesn't do anything to this. Define half-life as the time taken for radioactive activity to reduce to half to its original value, original activity. This is again a fixed definition. I can't really help you with this. Now this part is one of the parts that has been repeated repeatedly in the previous past papers. These are binding energies. This is before and this is after, and definitely the answers look the part. Why? Because the binding energy before the reaction is less, and after the energy after the reaction or after the nuclear process, it's higher. And that tends to why these nuclear processes are actually happening, because they're going from less stable state to more stable. Binding energy is definitely a representation of the stability of the nucleus. So for example, we have PO, that is 193, is destroying itself to become PB 189 plus alpha 42. This is 82, this is 84, and again the left side is less stable because its binding energy is low. The right side is more stable because its binding energy is high. Binding energy, if you simply add these numbers together, it will give you an idea. But anyways, we're not going to do that because its binding energy per nucleon, if you remember, is per nucleon. There are 193 nucleons in PO, 189 in lead, 1 and 4 in alpha. So the energy released will be something like this. So the delta E should be equal to 189 released energy, or 189 nucleons of lead, and the energy is given to us as 7.826 plus, because it's on the same side, 4 into 7.074, the alpha, minus some of the energy is taken back by the PO, which is polonium, of course, which is 193 nucleons at a binding energy of 7.774 per nucleon, of course. And this comes out as 7.03 electron volts per nucleon, right? Or the total energy that has been released in the process. So if you use the E equals to mc square, convert this energy back to the mass, you will finally realize that the extra energy that is being released in the process was actually brought in by the mass that disappeared and is converted into energy. But anyways, a pure sample of polonium is given to this, the equation is given to us, the graph is given to us, and the equation of the graph looks eerily similar. You see, it comes from the idea that n is equal to n naught e raised to the power minus lambda t. Okay, and we have looked at this equation before. If you notice, this is ln n by n naught. So let's bring this over here. So this becomes n over n naught equals e raised to the power minus lambda t. So we'll use this result later on. He says state the name of the quantity represented by the magnitude of the gradient, that's decay constant, and let's see why. He says determine half-life using figure 9.1. Let's do that. So we have two formulas, which is lambda is equal to ln of 2 divided by half-life. The other formula that we got now is going to be from n equals n naught e raised to the power minus lambda t. So ln of n divided by n naught gives me negative lambda t. If you compare this with y is equal to mx, you realize that this is your y-axis and this is your x-axis. So the gradient really, or the m really, is the decay constant. That's why over here we find it to be the decay constant. And now we're going to use this to find out the half-life. So let's pick out a value from the graph. What I've done is chosen this value because it's exactly 100% on the dot. You can choose any other value that's on the dot, but I like to choose the extreme values because it generally covers the whole graph. This is actually negative 1.4, and this is with milliseconds, so be careful. This is going to be, first let's calculate the gradient. The gradient is equal to negative 1.4 divided by 0.84 from the graph into 10 to the power minus 3, which is equal to ln of 2, because that's where we get this from, right? Divided by t half. And t half is going to be equal to 0.4158 milliseconds, which will be 0.42. It decays quite quickly. The decay constant is quite low. He says, give us the benefit of PET. He says, what happens to the positrons emitted by the tracer? And by this stage, we know that positrons collide with electrons in the body that are already present and annihilate. And after annihilation, they release two gamma ray photons in the opposite direction, which help us backtrack our way to the site of the tumor. That's why we do this PET scans. Part 2, explain why tracer has a half-life of approximately 2 hours, and then it's a decision between time versus exposure. It's long enough to conduct the experiment safely or successfully to locate the tumor, but it's not too long to cause damage to the patient. So it's always a bet. It's always a race against time. Okay, question number 10. State the luminosity of a star. So the power radiated by the star. If now standard candles are calculated, this is a standard procedure, 3-mark question. He says we know the standard luminosity of known stars, for example our own sun. We measure the radiant flux density F, and then we use the formula F equals. This is a standard answer for this question, which is a repeated part for this question. Now this is interesting. He says that the sun rotates like this, and the arrow is shown to you. There is center of the axis, and this is, for example, where you're standing. The light ray coming from this axis will exactly be with 100% accuracy, will have no change in speed. But the light coming from Z would be faster, or the wavelength will be faster. So this wavelength will be shorter. But the wavelength coming from X, this side, because it's rotating that way, wavelength coming from this side will be longer. It will have shorter energy, it will have slower moving photons, but the change is very slight. You see, is 2877 and 2831 as opposed to this one. So you can link that the observed from Y is the true wavelength. From X is Doppler shifted, and from Z it would also be Doppler shifted. But let's see how that goes. The sun rotates with a speed this, radius is this. He says show that the radius is this. Let's try this question. So first we need to find out the speed. So delta V using Doppler effect divided by V is partially equal to lambda d, change in lambda, divided by lambda. And delta V is what we're looking for. Speed is the speed of light, because we're dealing with light, equals the change in wavelength, which is 656.2877, what you just observed, minus 656.2831, divided by what is the true value, which is 656.2831. Notice that the comparison is with the wavelength that we observed at Y, and Y is at the center. This is the true wavelength that doesn't have any sort of Doppler effect. Okay. All right. So the del, and this goes over there, gets multiplied, and the reason I've not added nanometers is because it's in the numerator and the denominator, so its effect will be cancelled out. We're left with delta V equals to 2102 meters per second. And now we use the formula V equals 2 pi r divided by t. This will be 2102. 2 pi into r is supposed to be found out, and t is given to you as this. 2.07 into 10 to the power 6. And your r comes out as exactly 6.93 into 10 raised to the power 8 meters. The next part is state explain how the expected wavelength of the light is observed from Z compares with the emitted wavelength. Z is moving close to the Earth, hence observed wavelength is shorter than emitted. And I've already discussed this over here. This is already discussed due to Doppler effect. It says the luminosity of the sun is given to you, and it says use the information B1 to calculate the surface temperature. This is the Wien's displacement law sort of calculation. So this will be L equals 4 pi sigma r squared T4. So this will be 3.8 into 10 raised to the power 26 equals 4 pi. Sigma value is a constant, 5.67 into 10 raised to the power minus 8 into 6.93 into 10 raised to the power 8 whole square into 3 raised to the power 4. Now please be advised, again, if you weren't able to solve this part, please don't leave the rest of the question. You will need that value again. And look, you could still have gotten 2 marks. So this is 3 raised to the power 4. Don't forget to take the fourth root on the other side. This will come out as 5800 Kelvin. This is your final answer. And that is all for today. That is your final last question.